Hello friends, we are going to continue our discussion on Fermi surface. We already know how to draw first, second, third and fourth Brillouin zone of a square lattice. In this lecture, we are going to learn about drawing the Fermi surface in different Brillouin zones of a square lattice starting with free electrons. Let us write a Python code to plot the Fermi surface of 2D free electrons. Note that this is an empty lattice approximation because we are going to use the Brillouin zones of a 2D square lattice while plotting the free electron Fermi surface. The energy dispersion relation is given by E is equals to h cross square by 2m times kx square plus ky square. Setting h cross square by 2m equal to 1, I calculate the energy in this line of the code. We have plotted this quadratic surface before. This time, in addition to the surface, we also plot the energy contours. This is the code to plot the energy contours. This is where I define the range of kx and ky, and the range is extended slightly beyond the first Brillouin zone. This is where I calculate the energy. This is where the quadratic surface is plotted, and this is where the energy contours are plotted. Let us run the code. Energy contours are constant energy lines. It is a constant energy surface drawn in the reciprocal space. For 2D free electrons, Fermi surface is one of the circles shown in this diagram. All the states lying outside the Fermi surface are empty, and all the states lying inside the Fermi circle are full. Radius of the circle is given by kf is equals to 2 pi n whole to the power half, where n is the number of electrons per unit area. Thus, radius of the Fermi surface depends on the electron density. Higher the electron density, more will be the radius. Take a small electron density such that radius of the Fermi surface is short. For example, this one. The red dashed line show the boundary of the first Brillouin zone. Thus, if the Fermi surface has a short radius, it will lie completely within the first Brillouin zone. Consider higher electron density such that the radius of the Fermi surface is large. For example, this one. In this case, part of the Fermi surface lies within the first Brillouin zone and part of it lies outside the first Brillouin zone. In conclusion, the Fermi surface, a circle in case of 2D free electrons, may get extended beyond the first Brillouin zone or any other Brillouin zone depending on the electron density. Let us understand how reduced zone scheme work in case of 2D. This is the quadratic energy surface for free electrons. In certain regions, I have extended it beyond the first Brillouin zone. Regions within the first Brillouin zone are shown by the red border. Let us select some region beyond the first Brillouin zone. Let's say this region and shade it with some other color. Now, this region is lying outside the first Brillouin zone, and let me bring it inside the first Brillouin zone. Similarly, I select another region which is lying outside the first Brillouin zone and shade it with some other color. And again, I bring it inside the first Brillouin zone. Now, below the red border, we have the first band, and above the red border, we have the second band shown by the red shaded regions. Now, both of them are drawn in the first Brillouin zone as per reduced zone scheme. Thus, we know that constant energy contours may span more than one Brillouin zone depending on the electron density. A constant energy contour going beyond the first Brillouin zone, what does it mean? It implies that certain regions of the second band has same energy as certain regions in the first band, at least in case of empty lattice model, which deals with free electrons. In fact, certain regions in the second band can have lower energy than certain regions in the first band. For example, in the right hand side diagram, red region in the top is the second band. Remember that the second band is the part of the quadratic energy surface which was originally in the second Brillouin zone and has been brought to the first Brillouin zone as per reduced zone scheme. Clearly, this region of the second band or this region of the second band has less energy than this region of the first band. This is known as band overlap. Let us try to understand band overlap in terms of EK diagram. Top figure shows the Brillouin zones of a 2D square lattice. Bottom figure in the left shows the quadratic energy surface for free electrons in reduced zone scheme. The blue surface is the first band and the red surface is the second band. Remember that the red surfaces were lying originally in the second Brillouin zone and have been brought to the first Brillouin zone as per reduced zone scheme. This figure is the EK diagram along the high symmetry points in the first Brillouin zone. The blue lines correspond to the first band. They correspond to the energy within the first Brillouin zone. The red lines correspond to the second band. They correspond to energy values in the second Brillouin zone. Similarly, the green and the magenta line corresponds to energy values in the third and fourth Brillouin zone. Clearly, within this energy window, part of the first band and second band have same energy. Thus, we can say that the first and second band overlap. This becomes very clear in the energy band diagram as shown here. Band 1 and band 2 has some overlap in certain energy window. Let us now draw the Fermi surface for a monovalent metal. In case of a monovalent metal, area of the Fermi circle is half the area of the Brillouin zone. Thus, the Fermi circle lies completely within the first Brillouin zone. In the EK diagram, this is the Fermi energy. And note that the Fermi energy line crosses only one band, the first band. This also implies that the Fermi circle lies completely within the first Brillouin zone. If we repeat this diagram like we did for periodic or repeated zone scheme, then this is what we get. Now, let us draw the Fermi surface of a divalent metal. In case of a divalent metal, area of the Fermi circle is equal to the area of the Brillouin zone. Now, if we draw the Fermi circle, which has same area as the Brillouin zone, it crosses over from the first Brillouin zone to the second Brillouin zone. In the EK diagram, we also find the line corresponding to the Fermi energy crosses two bands, the first band and the second band. This also implies that the Fermi circle goes beyond the first Brillouin zone and crosses over to the second Brillouin zone. Let me show how to draw the Fermi surface in different Brillouin zones in this case. The red box denotes the first Brillouin zone and the blue box denotes the second Brillouin zone. Clearly, the Fermi circle crosses over from the first Brillouin zone to the second Brillouin zone. In this diagram, I show only the part of the Fermi circle inside the first Brillouin zone. And in this diagram, I show the part of the Fermi circle outside the first Brillouin zone. Now, let me bring this portion from the second Brillouin zone to the first Brillouin zone. Similarly, let me bring this portion from the second Brillouin zone to the first Brillouin zone. Now I bring this portion from the second Brillouin zone to the first Brillouin zone. And finally, I bring this portion from the second Brillouin zone to the first Brillouin zone. I just followed the reduced zone scheme. Now, let me apply the repeated zone scheme and repeat the Brillouin zone periodically in space. For example, I take this Brillouin zone and I repeat it in space like this. Similarly, I can do it for the first Brillouin zone. Thus, this is how the Fermi surface looks like in the first Brillouin zone, and this is how the Fermi surface looks like in the second Brillouin zone. Now, let us draw the Fermi surface of a trivalent metal. In this case, area of the Fermi circle is equal to 1.5 times the area of the Brillouin zone. If we draw the Fermi circle, obviously it crosses the first Brillouin zone and goes to the second Brillouin zone. However, it does not cross over to the third Brillouin zone. In EK diagram also, we find that the line corresponding to the Fermi energy crosses the second band but does not cross the third band. This implies that the Fermi circle does not cross over to the third Brillouin zone. Let me show how to draw the Fermi surface in different Brillouin zone. In this diagram, I show the portion of the Fermi circle only within the first Brillouin zone. This is not so interesting as the first Brillouin zone is completely occupied. In this diagram, I show the portion of the Fermi circle lying outside the first Brillouin zone. Let me bring this portion from the second Brillouin zone to the first Brillouin zone. Now, let me map this portion from the second Brillouin zone to the first Brillouin zone. Then I map this portion from the second Brillouin zone to the first Brillouin zone. And finally, I map this portion from the second Brillouin zone to the first Brillouin zone. I just followed the reduced zone scheme while mapping from the second to the first Brillouin zone. Now, let me apply repeated zone scheme and repeat the Brillouin zone periodically in reciprocal space. So, I take this object and repeat it periodically in space. Repeat it periodically in space. And repeat it periodically in reciprocal space. In case of a trivalent metal, the first Brillouin zone is completely full, and this is how the Fermi surface looks like in the second Brillouin zone. Finally, let me show you how to draw the Fermi surface for a tetravalent metal. In this case, area of the Fermi circle is twice the area of the Brillouin zone. When we draw the Fermi circle, it extends all the way to the fourth Brillouin zone. In EK diagram also, we find that the line corresponding to the Fermi energy crosses the second, third, and fourth band, which implies that the Fermi circle extends to the second, third, and fourth Brillouin zone. Let me show how to draw the Fermi surface in different Brillouin zone. In this diagram, I show the part of the Fermi circle only within the first Brillouin zone. It is completely full and not so interesting. Next, we show part of the Fermi circle in the second Brillouin zone. I map each portion back to the first Brillouin zone one by one, starting with this, followed by this, this, and this. In this diagram, I show the portion of the Fermi circle lying in the third Brillouin zone. As I did for the second Brillouin zone, in this case also, I map each portion to the first Brillouin zone. So, this portion is mapped to the first Brillouin zone. Next, this portion is mapped to the first Brillouin zone. Next, this portion is mapped to the first Brillouin zone. Next, this portion is mapped to the first Brillouin zone. Next, this portion is mapped to the first Brillouin zone. Next, this portion. Next is this portion. And finally, we map this portion to the first Brillouin zone. In this diagram, I show the portion of the Fermi circle lying in the fourth Brillouin zone. Again, I map each portion back to the first Brillouin zone. So, this portion is mapped to the first Brillouin zone. This portion is mapped from the fourth Brillouin zone to the first Brillouin zone. this portion is mapped from the fourth Brillouin zone to the first Brillouin zone, and finally this portion is mapped from the fourth Brillouin zone to the first Brillouin zone. After mapping the portions of the Fermi circle lying in higher Brillouin zone to the first Brillouin zone according to the reduced zone scheme, I apply periodic zone scheme and repeat each Brillouin zone periodically in reciprocal space. So let me start with the second Brillouin zone. I take this portion and repeat it periodically in reciprocal space. Take this portion and repeat it periodically in reciprocal space. Take this portion and repeat it periodically in reciprocal space. Then I do it for the third Brillouin zone. Take this portion, repeat it periodically in reciprocal space. Take this portion and repeat it periodically in reciprocal space. Take this portion and repeat it periodically in reciprocal space. Then I do it for the fourth Brillouin zone. Take this portion and repeat it periodically in reciprocal space. Repeat it periodically in reciprocal space and repeat it periodically in reciprocal space. In case of a tetravalent metal, the first Brillouin zone is completely full, and this is how the Fermi surface looks like in second, third, and fourth Brillouin zone. It is not an easy task to show how to draw Fermi surface in 3 dimensions. However, let me illustrate one simple example. I draw the Fermi surface assuming Brillouin zone of a simple cubic lattice. Fermi surface is spherical for 3D free electrons. If we have a monovalent atom, then the Fermi surface does not cross the first Brillouin zone boundary. Volume of the Fermi sphere is equal to the half the volume of the Brillouin zone. The Fermi sphere is a spherical surface lying completely within the first Brillouin zone. In case of a divalent metal, volume of Fermi sphere is equal to the volume of the Brillouin zone. It crosses the boundary of the first Brillouin zone. As a result, part of the Fermi surface lies in the first Brillouin zone and part of it lies in the second Brillouin zone. This is how the Fermi surface looks like in the first Brillouin zone, and this is how it looks like in the second Brillouin zone. So far, I have drawn free electron Fermi surfaces. However, periodic potential may deform the free electron Fermi surfaces. We are going to learn how to draw Fermi surfaces in case of a weak periodic potential in the next lecture. Fermi surfaces for the actual metals can look like spherical Fermi surface of free electrons for some metals. However, for most of the metals, it looks very complicated. To get a feeling of how the Fermi surface looks like for actual metals, you are advised to visit this website.